The loss of TB-29 Superfortress serial number 4470039 demonstrates how little margin alpine navigation allowed under severe weather constraints. Operating out of Elmendorf Air Force Base in November 1957, the crew entered a routine ground radar calibration flight designed to test regional defense networks. Public accounts do not prove a single instrument failure. They establish a bomber descending in poor weather with positional certainty degraded. The aircraft was reported to have followed non-directional radio beacons, and without visual cross-references, the crew's assumed position could separate from the bomber's true position over the ground. The aircraft was assigned to the 5040 Radar Evaluation Unit at Elmendorf Air Force Base. Published accident summaries identify the organization as the 5040 Radar Evaluation Squadron, while a JBER historical account identifies it as the 5040 Radar Evaluation Flight. The flight plan dictated an 1,800 nautical mile circuit intended to test radar stations across the northern sector. The crew prepared for a 10-hour flight operating under instrument flight rules. Weather across the high altitudes brought a low ceiling, dense cloud cover, and light snowfall, leaving the crew dependent on instruments while the mission profile demanded precise alignment with approach corridors back into the anchorage area. Radar calibration required rigid adherence to planned tracks so the ground stations could receive accurate target data. Under shifting winds and limited radio beacon fidelity, that precision requirement became the central vulnerability in the navigation plot. In that navigation environment, even a modest, uncorrected crosswind could leave the indicated heading looking stable, while the bomber's true ground track moved laterally over the course of the mission. The flight crew appears to have believed they were positioned on the northern approach toward the anchorage area. The available accounts do not prove exactly what the instruments showed inside the cockpit, or the exact sequence of decisions made there. Public evidence only establishes that the crew was descending in weather, badly displaced from its intended course, and following a standard descent profile without recovered cockpit or flight recorder data to explain why. The aircraft crossed the 27-mile lateral error boundary and entered the high peaks of the Talkeetna Mountains. The divergence meant the descent path intersected a solid terrain mass rather than open approach airspace. Ground controllers lost radar contact when the bomber dropped below the mountain ridges, giving rescue coordinators a final plotted reference point. Rescue planners could combine that lost contact point with the reported route, the 10-hour schedule, and remaining fuel assumptions to narrow the initial tracking box. Despite the massive 27-mile navigation error, this perimeter focused the search toward the eastern mountain ranges, where the standard descent had intersected an unnamed glacier instead of open approach airspace. How does a massive aluminum bomber survive a direct impact with a rising mountain of solid ice? The impact geometry defined the boundaries of the wreckage site. Reported accounts describe the aircraft striking the glacier at about 5,600 feet in a near-level attitude rather than driving directly into a vertical rock wall. Instead, the flight path intercepted the sloping glacier at a shallow angle. The mechanism governing this destruction is controlled flight into rising terrain, not a single vertical impact. When an aircraft impacts a rising incline at a flat angle, the forward kinetic energy can convert into sliding motion along the surface rather than forming a singular crater. This physical reality can force the resulting debris field to spread linearly across the terrain. For the trainer aircraft, this shallow intersection meant the tubular center section of the fuselage remained largely intact as it plowed forward. The forward momentum required an enormous dissipation of energy, which was achieved through the structural failure of the wings. As the massive bomber slid upward along the solid ice, the airframe underwent kinematic separation. Uneven terrain resistance forces high drag outboard components to shear away from the main structural tube. The nose gear took the initial impact and sheared off almost immediately upon contact with the glacial ice. The four massive engine nacelles, the heavy main landing gear assemblies, and the wings caught against the rough, frozen surface and were ripped from the central body. That sequence left the main cylinder less exposed to inward crushing as the separated components absorbed the worst of the breakup loads. The kinetic sequence dispersed the wreckage across a wide footprint. The heavily reinforced center section traveled 150 feet up the glacier before friction finally arrested its movement. The intense structural forces involved in shedding the wings completely severed the forward fuselage from the main cabin. This detached nose section carried its own forward momentum, continuing its trajectory away from the main wreckage. The nose structure slid an additional 200 to 500 feet further up the steep slope before coming to rest. This distinct linear slide sequence generated a positive knowledge gain for military investigators. Those separated components marked successive stages of breakup across the glacier. Public accounts do not support a perfectly fixed map of every component's original position, but the physical layout still preserved the aircraft's broad deceleration sequence. While the shallow impact preserved the main fuselage, the final resting place established a permanent operational boundary. The physical state of the stripped wreckage combined with its location created a severe logistical constraint. The remaining aluminum tube weighed thousands of pounds and sat immobilized deep within a rugged, high alpine glacier environment. At 5,600 feet, the weight of the structure, the steep, crevassed ice, and the surrounding rock walls made heavy airlift or ground extraction impractical. The institutional trade-off was therefore clear. The immediate priority became locating the crew before weather erased the approach window. With the fuselage immobilized on the ice, how could search teams locate the wreckage before the blizzard buried it completely? The crash was reported at approximately 18:22 hours, shortly after the aircraft began its descent. That timestamp established a brutal operational window for military coordinators. Nightfall over the Talkeetna Mountains coincided with an incoming severe blizzard, creating an impenetrable operational boundary across the entire region. Extreme alpine weather completely blocked immediate nighttime access to the suspected crash zone. Search aircraft were grounded due to zero visibility, and overland rescue teams could not safely navigate the shifting ice crevasses or steep, avalanche-prone terrain in total darkness. The military rescue coordinators were forced to hold their primary assets until dawn. They had to balance the urgency of the missing crew against the extreme risk of deploying search assets into a blind, frozen environment. When daylight finally broke the following morning, the weather system cleared just enough to launch visual reconnaissance flights. The search coordinators designed an aerial grid based strictly on the final radar plot from the previous evening. They deployed an SA-16 Albatross amphibian aircraft to sweep the eastern peaks. Flying at low altitude, the search crew scanned the white terrain looking for the distinct metallic contrast of an unpainted bomber hull against the glacial snowpack. Spotting aluminum wreckage in a whiteout alpine environment requires intense visual discipline, as the blowing snow quickly obscures structural outlines. The amphibian crew successfully spotted the shattered aircraft resting high on the mountain slope. This visual identification represented a critical positive knowledge gain for the investigation. Locating the wreckage achieved the immediate primary search objective, pinpointing the exact coordinates necessary to vector specialized recovery assets directly to the target. With the site accurately localized, the mission pivoted immediately from a wide-area search to a precision extraction sequence. Standard fixed-wing aircraft could not operate within the tight mountain valleys or attempt a landing on the heavily sloped, deeply crevassed glacier. The military deployed 2 SH-21 workhorse helicopters to execute the recovery phase. Operating rotary wing aircraft at high altitudes introduces severe procedural constraints. As elevation increases, air density decreases, forcing helicopter rotors to work harder to generate sufficient lift. The workhorse helicopters navigated treacherous mountain weather and thin air to reach the wrecked bomber. Public accounts identify the SH-21 crews as the recovery aircraft that brought the survivors off the mountain, but they do not document every landing, loading, or power setting detail. Once the rescue helicopters cleared the mountain, the operation transitioned from an active recovery mission to a permanent site management problem. The heavy bomber structure remained firmly anchored to the ice. No public source reviewed here confirms a classified equipment recovery requirement or a formal environmental cleanup decision for the remaining airframe. What the record does show is narrower. The survivors were rescued, the dead were accounted for, and the heavy wreckage was left on the glacier. That decision turned the crash location into an abandoned high alpine site exposed to the mountain environment. Once the helicopters departed, what critical structural evidence was left, preserved inside the aluminum tube. Evidence initially establishes a strict division in the outcome of the 10 crew members. Published accounts report that 6 crew members were killed in the crash, while 4 personnel survived the initial impact sequence. What remains uncertain is the exact chronological movement of the crew inside the aircraft during the violent deceleration. However, why this sequence matters procedurally is fully documented by the physical state of the wreckage. The immediate post-impact environment created a lethal hard limit. With the blizzard preventing extraction, the operational priority inside the wreckage shifted from waiting for rescue to raw thermal management. The primary anchor of proof for this survival timeline rests entirely on the coherent evidence of the center fuselage section. Because the shallow impact angle spared the main cabin from total crush destruction, the unpainted aluminum tubular structure retained its fundamental geometry. This heavy structural shell proved critical. It provided a rigid, windproof enclosure that shielded the interior volume from direct blizzard exposure. If the fuselage had shattered completely, the total loss of a windbreak would have resulted in rapid, irreversible hypothermia for anyone exposed on the open ice field. Instead, the surviving structural envelope offered a baseline geometry to establish a defense against the Arctic environment. Inside that shell, the next problem was conductive cold. The bare aluminum flooring and bulkheads could draw heat away from injured survivors even with the wind blocked. Staff Sergeant Calvin K. Campbell, operating in darkness and severe weather despite his own injuries, sought out the other survivors, moved those who could be moved toward shelter, and helped protect them inside the wreckage. Moving the survivors out of the direct storm was only the first necessary procedural step. To halt the conductive heat loss, Campbell implemented a rigorous method of improvised insulation, establishing the method fingerprint of the survival effort. Utilizing the remaining operational inventory inside the wrecked cabin, he gathered heavy canvas covers, standard-issue cargo sleeping bags, and attached nylon parachutes. By layering these textiles directly over the freezing aluminum floor, he constructed a definitive thermal boundary between the metal and the survivors. Wrapping the injured personnel in the remaining parachutes trapped a small insulating air layer around their bodies. This material improvisation was the decision point that extended the survival window through the night. The current preserved state of the center section provides a narrow proof limit for the survival timeline. It confirms that shelter was physically possible, but public accounts do not document a formal post-recovery analysis proving a precise fatal exposure threshold before dawn. While the main cabin held its shape, where did the severed nose section and high drag components ultimately come to rest? The physical distribution of the wreckage presents an immediate documentation challenge. Public accounts describe an aircraft that slid and broke apart across the glacier, while modern visitors see a site altered by exposure, seasonal snow, and gradual glacier movement. The visual survey of these detached elements forms the foundation of modern site documentation, separating what can be measured today from what the mountain has altered over time. The survey grid relies entirely on locating the detached components across the wide footprint. The 4 separated R-3350 radial engines, the landing gear debris, the center fuselage, and the severed nose section define the visible debris field. Documenting this linear distribution verifies the broad vector of the debris path across the ice without requiring every heavy component to mark the original lower boundary of the wreckage zone. Recording the spread between the major components defines the measurable bounds of the site as it can be observed today. However, interpreting this debris footprint requires treating the glacier itself as an active survey variable. Over decades, that moving ice can carry, expose, or partly bury aircraft components, establishing a rigid proof ceiling for any modern site survey. Investigators cannot treat present-day debris positions as a precise map of the original crater, or the primary point of structural failure. Moving ice, snow cover, and surface change have likely blurred the first impact scar, leaving surveyors able to confirm the general vector of the event, but not exact 1957 component positions. Evidence discipline therefore shifts the survey away from exact reconstruction and toward documented present condition. The sheared nose gear strut remains visible and confirms an early separation event, while observers focus on cataloging material degradation and changing component positions. With the wreckage slowly moving down the mountain, what is the ultimate management fate of this frozen site? The abandoned surplus trainer airframe created a long-term environmental footprint beyond the immediate recovery crisis of 1957. Today, the wreckage has transitioned from a military recovery problem to a wilderness stewardship and memorial concern. Visitors and local managers widely treat the site as an informal historical memorial on public land. If the wreckage is managed as a historic resource on state land, disturbance or removal would require authorization rather than casual collection. This memorial status makes the management boundary practical as well as legal. The wreckage should be left alone, and any authorized work must pass through agency review. This hands-off management approach has yielded a specific positive knowledge gain regarding aerospace material longevity. Because the site remains undisturbed by active recovery operations, observers can accurately document the interaction between aviation-grade metals and the severe alpine climate. Modern survey objectives focus exclusively on establishing a baseline condition assessment of the remaining hardware. Over decades of visual monitoring, the condition of the metal verifies the unique protective qualities of the high-altitude glacier. The cold alpine setting has helped leave much of the wreckage visually recognizable. While lower elevation sites can degrade quickly under vegetation, moisture, and human interference, this glacier site still preserves a striking amount of aircraft structure. The public record supports that visible durability, but not a detailed corrosion study of the bomber's aluminum alloys. The strongest visible anchor is the surviving military insignia on the exterior. Despite heavy annual snowfall, abrasive high-velocity winds, and intense ultraviolet exposure for more than half a century, the painted lettering remains legible across the unpainted metal cylinder. For modern surveyors, that marking provides a fixed visual reference in the stark white landscape. The final management reality is non-intervention. No public source reviewed here indicates an active project to remove the site, erect physical shelters, or apply chemical conservation treatments to the bare metal. The sheer mass of the remaining fuselage and the terrain at 5,600 feet keep the logistical barrier high enough that the airframe remains in place. As the glacier continues its slow descent, how long will the mountain preserve the evidence of this cold zone operation?